All right, so we've been learning all about rate laws, all about concentrations and how to determine rate laws given a handful of experiments, right? Finding out how the rate of a reaction changes by doubling a given reactant, for example. Now, the rate laws relate the rate of the reaction to the reactant concentrations. Because the values of K varies with temperature, so will the rate law, okay? The value of K varies with temperature. The rate law will also change with temperature. Just a good piece of information to keep in mind. So we would also like to what we call integrate the rate laws so that at any given moment of time we can identify how much of the given reactants are left in a chemical reaction. All right, and we can do this. Well, we have equations that relate the concentration of reactant versus time, and those concentrations, or those equations, differ for a zero-order reaction, and a first-order reaction, and a second-order reaction. Okay. So for a zero-order reaction, if you plot the reactant concentration versus time, you'll get a linear relationship. For a first-order reaction, you need to plot the natural log of the reactant's concentration versus time to get a linear relationship. And for a second-order reaction, you need to plot 1 over the reactant concentration versus time to get a linear relationship. Okay, so that's our first introduction to this, recognizing that there are different ways to get linear relationships, and we always want to have a linear relationship because that'll tell us information about the chemical reaction. But let's get into this a little deeper and look at what the zero-order reactions, the integrated equation, integrated rate law for the zero-order reaction is. The rate law for a zero-order reaction is just rate equals K.
Where's the concentration for the reactants?
Well, if we were to include them, because it would be zero order with respect to those concentrations, it would just be something like this. Rate equals little k times, let's say the reactants are called A and B. But if it's zero order with respect to our reactants, then both A and B are going to be raised to the 0, and so they fall out of the equation. So the zero-order reaction's rate law is always going to be rate equals whatever the rate constant is. And if we plot the reactant's concentration versus time, again, you'll get a linear relationship. So the concentration of A versus time, right, if this is our reactant here, it will just decrease over time. And the rate at which it decreases is independent of how much A there is. So as the concentration of A changes, the rate stays exactly the same because there's no rate dependence. And that's what a zero-order reaction is. And the equation of this line here will be in this form here where you have your Y equals mx, and it's a negative slope, plus B, right? So again, y equals mx plus b. That will be the equation for a zero-order rate law, where m is the slope, concentration versus time. That's the rate, and that rate here is expressed as k because that's it. The rate is equal to k. For whatever time you provide, and you multiply it by the slope, right? So if I provide this many seconds, for example, and I give this slope, I can identify what the concentration of A is going to be, given that this is our y-intercept, right, our B value. And the y-intercept is the initial concentration of the material. And the initial concentration, we use this little naught value. That means time equals 0. And where time equals 0, that's the initial concentration of our reactant here. All right. So these reactions are diffusion controlled. The reaction just goes as fast as the material can flow around. The rate is independent of the concentration of the reactions, but the reaction still requires reactants to proceed, right? You got to have something for there to produce products. So with that information in mind, the rate law for this chemical reaction is zero order, let's say, and has a rate constant of 0.02 molar per second. If the reaction starts with 1.5 molar A, how much is present 15 seconds after the reaction begins? Well, can you provide me the rate law for this reaction first, Fred?
The rate law. Well, it's going to be rate equals
That's right, very good. That's how all rate laws start. Rate equals
K times the concentration of reactants A. Well, I guess A is to the 0 though, right?
That's right. So in a way, the rate law is just rate times K, right? And make sure I emphasize that that's a lowercase k. All right. Now, the question is, if the reaction starts with 1.5 molar A, how much is present after 15 seconds?
Well, I don't know how to do that.
Well, we have to think about the integrated rate law, which is that the concentration of A will be equal to whatever the concentration you start off with minus the rate times how long you've let the reaction proceed. Right? Can you see that? The concentration of A will be, now if you didn't let the reaction proceed, if T was equal to 0 here, you would subtract K times 0, which is 0. So these two would be equal. But for every second that you let the reaction go, then 0.02 molars per second will be removed from our initial concentration. So we have our initial concentration of 1.5 subtracting 0.02 molar per second. This is a molar, right? And we're going to let it proceed for how many seconds?
15 seconds.
15 seconds. Very good. So 15 times 0.02, 0.3 molar. So 1.5 minus 0.3. So we're going to get 1.2 molar is left over. How much is present 15 seconds after the reaction? It's going to be 1.2 molar. Okay, did you see that?
Yeah, I see that. How am I going to remember that rate law, though, or that integrated rate law?
Well, what we have to remember first is that when the reaction is zero order, the plot of the concentration of a reactant versus time will be a linear relationship. And that y equals mx plus b, where m is the slope, concentration versus time, right? Or that's the rate of the reaction. So we realize that it's going to be k because a zero order reaction is always rate equals k. Y, that's our initial concentration, y naught. X, that's going to be our time there, right? And b is going to be, oh no, sorry, this isn't y naught. That's just a. B, the y-intercept, that's going to be the a naught, okay? And so again, we have here the rate plus a rate times t plus a naught, and this is going to be a negative rate always. You don't have to throw in the negative. You can just find out what the rate is, and it'll produce a negative value. But the k value is going to be a positive value, so we throw in the negative because of the slope here. But that is where this rate law comes from, knowing that the relationship between zero order and for a zero order reaction, the relationship between concentration and time is linear. Okay, Here's another opportunity. Why don't you guys try this one at home and push pause, try this one at home and see what you get. Okay, push pause hopefully. Try it for yourself. Got to make sure you take these opportunities to exercise. The rate law for the reaction this here is zero order with respect to A and has a rate constant of 0.12 molar per second. If the reaction starts with 1.5 molar, after what time will the concentration of A be 0.9 molar? All right. Same thing. We have our zero order rate law, right? The A at any given time, sometimes they put a T down there, equals the A naught minus the rate times the concentrate or the time that you let that reaction proceed. So we start off with 1.5. We're wondering how much time is going to have to pass to get 0.9 minus the rate here, 0.12 times, I'll put in a x value for t there. Okay, so if we solve this, it looks like we're supposed to get 5. We can put this in the calculator just in case it's confusing for people. 0.9 subtracting 1.5 divided by negative 0.12. All right, 5 seconds. Excellent. Okay, zero order rate law. Good place to stop.